In this circuit, we are to calculate the value of the capacitor needed to obtain a circuit power factor of 100%. This is known as power factor correction. S is the apparent power. Before power factor correction can be calculated using P divided by cos theta, we must be given P and cos theta, which we are. Plugging those values into our equation, we get 1200 divided by 0.7, which equals 1714 VA. Hence, the magnitude of the motor current, I, is simply S divided by the magnitude of the voltage E, which equals 1714 VA divided by 120 volts, and that equals 14.29 amps. This is designated as IM in our diagram. The active component of this current is the component in phase with the voltage. This component, which results in true power consumption, is IM cos theta, and that's equal to 14.29 amps times 0.7, which equals 10 amps. Because the motor has 70% power factor, the circuit must supply 14.29 amps to realize a useful current of 10 amps. In order to obtain a circuit power factor of 100%, the reactive power of the motor, which we know is inductive, and the reactive power of the added capacitor must be equal. The reactive power of the motor, QL, which is equal to the magnitude E times the magnitude I times the square root of the quantity 1 minus cos squared theta. Now, where did this come from? This is known as an equation for calculating reactive power. Let's go through a quick review of how it is obtained, starting with the power triangle, which tells us that the apparent power S supplied to the load may be calculated by the product of the magnitude of the supply voltage E times the magnitude of the supply current A. The true power P then is equal to the magnitude A times the magnitude A times cos theta, and the reactive power Q is equal to the magnitude of E times the magnitude of A times sine theta. There is a trig function that exists from the study of the unit circle, which states that the sine squared theta plus cos squared theta is equal to 1, where theta can be any angle. This means that sine squared is equal to 1 minus cos squared theta, and sine theta then is the square root of 1 minus cos squared theta, which means this is equal to E times I square root of 1 minus cos squared theta, and that is how we obtained the equation for QL. Knowing where the formula came from, we can see that the square root of 1 minus cos theta is equal to the reactive factor. Sine theta, plugging in our known values, we get QL equal to 120 times 14.29 times the square root of the quantity 1 minus 0.7 squared. This reduces to 1714, the square root of 0.51. which works out to 1,224 VARs inductive. Let's for the moment return to the power triangle, keeping in mind that the power factor angle is also the angle between the applied voltage and the current in the circuit. Remember that the formula for complex power is VI conjugate. Remember now that these terms are phasors or vectors. And just to quickly review what a vector conjugate is, if the vector if the vector I, for example, shown here, is described by the magnitude I at plus theta degrees, its conjugate is the mirror image reflected across the x-axis, described by the magnitude I at minus theta degrees. There is an identity that we will be using regarding conjugate vectors. If we multiply a vector by its conjugate, such as I times I conjugate, that is the same as multiplying I at plus theta degrees times I at minus theta degrees, which is equal to I times I at 0 degrees, or I squared at 0 degrees, which is often designated without the degree indication as simply I squared. Returning to our power triangle diagram at the top, Ohm's law tells us that the voltage phasor V is equal to the current phasor I times the impedance phasor Z. Rearranging the terms of the equation, we can let I equal to V divided by Z. This equation can also be used to describe the relationship of the conjugate values. I conjugate is equal to V conjugate divided by Z conjugate. We can now rewrite the formula for complex power, substituting for the conjugate. S is equal to V times V conjugate divided by Z conjugate, or S is equal to V squared divided by Z conjugate. Now let's assume that our circuit contains only reactive impedances. That means the impedance Z is made up of only reactive components, X. Therefore, the apparent power will be equal to the reactive power Q, and the impedance conjugate Z is equal to the conjugate X conjugate. Our formula for apparent power can be rewritten as Q is equal to the square V magnitude squared all over X conjugate. Or rearranging the terms mathematically, we get X conjugate is equal to the magnitude V squared all over Q. And finally, this formula means that the magnitude of the reactance X is equal to the magnitude of the voltage squared divided by the magnitude of the reactance. Plugging in our known values of this formula, 120 squared divided by 1,224, or 11.76 ohms. Remember, this is the reactive, that is, to offset the induction of the motor, so it is capacitive. Remembering that the magnitude of the capacitive reactance is given by the formula XC is equal to 1 over 2 pi FC. Remember that we are trying to find the magnitude of the capacitor. Therefore, we bring our unknown capacitance to the left of the equation and all of the other quantities or known quantities to the right-hand side of the equation. And we get C is equal to 1 over 2 pi F times XC. Now we can plug in our known values, and we get C is equal to 1 over the quantity 377 times 11.76, which finally gives us the value of the capacitor, which is 255.5 microfarads. Of interest to this problem is what is happening to the currents in the circuit. The amount of current required by the load determines the sizes of the wire in the windings of the generator or transformer and in the conductors connecting the motor to the generator or transformer. Because copper losses depend upon the square of the load current, a power company finds it more economical to supply 10 amps at a power factor of 100% than to supply 14.29 amps at a power factor of 70%. A mathematical analysis of the currents are as follows. The magnitude of IC is equal to QC all over VC. The currents flowing in the capacitor is, using the values that we have at hand, equals 1,220 VARs divided by 120 volts, which has a magnitude of 10.2 amps, or in terms of a phasor, it is 0 minus J 10.2 amps. This is the current flowing in the capacitor branch. We already calculated the corrected current flowing from the 120 volt power supply as 10 amps, and it is at unity power factor because that's what we intended it to be. The current flowing to the motor lags the voltage because the motor has an inductive element. We can calculate that lag angle, let's call it theta, because we're given the power factor of 70%. Therefore, it is the inverse cosine of 0.7, which is 45.6 degrees. Therefore, the motor current IM is 14.29 at 45.6 degrees, or in rectangular coordinates is 10 plus J 10.2 amps. Clearly, the reactive part of the motor current is made up of the sum of the motor inductance current plus the capacitor current. That equals 10 plus J 10.2 plus the quantity 0 plus J 10.2, which equals 10 at 0 degree amps, 100% power factor. Typically, power factor correction capacitors are rated in kVARs or kilovars and may be installed in switched banks to provide a range of power factor correction. The reactive current flowing in the circuit is between the inductance of the motor and the capacitor. These currents are 180 degrees out of phase and oscillate such that the current flowing from the source is at unity, as can be seen. The current magnitude in any of the branches at no time exceeds 10.2 amps. In recent years, the reality of climate change has become impossible to ignore. Severe weather events, floods, tornadoes, violent storms are growing more frequent and more intense. For homeowners, this means that the utility power outages are no longer a rare inconvenience. They can last for hours, days, or in extreme cases even longer. The question is no longer if, but when you'll need a solution to keep your home powered and your family safe. When it comes to residential power backup, EcoFlow offers a range of solutions suitable for everything from powering a single appliance during a short outage to running an entire home in the event of an extended blackout. You can have a look at all of these options that are available by simply going to this web address.